Namaste and welcome. I am Vidyadhar, systems engineer, educator, and the creator of the Pragmosophy framework. In this 15-minute video, I will walk you through with the basic concepts of systems. Have a look at this particular diagram shown on the screen. This we term it as holon, and the whole discussion will be centered along with the concept of holon. We live in a world full of patterns and connections. Whether we look at the stars moving through the night, the way people organize themselves in communities, or how businesses function, we notice that nothing exists entirely on its own. Everything seems linked to something else in one way or another. Systems theory is a way of helping us to see and understand these links across every domain of life and knowledge. At its core, a theory is like a map. It gives us a structured way of thinking, helping us navigate in the complexities of the world. A theory does more than merely describe what we see. It helps us to create new ideas, identifying patterns, and sometimes even predict things that haven't happened yet. In this sense, a theory is a formal object. It creates new objects of thought and helps us to connect them in meaningful ways. The gravitational theory, for instance, it describes how objects with mass attract one another. Thanks to this theory, we can predict the orbits of planets, design satellite trajectories, and even explain why apples fall from trees. The theory gives us formal objects, such as the concept of mass, and formal links, such as the force of gravity acting between masses. Or consider the Maslow's theory in psychology. Maslow introduced the idea of hierarchy of human needs, suggesting that people strive to satisfy their basic needs like food and safety before moving on to social belonging, esteem, and finally to self-actualization. Here again, we see a theory creating formal objects, various human needs, and formal links between them, in the sense of one level depending upon the fulfillment of another. Systems theory is a bit different from specific theories like these because it isn't confined to one subject area. Instead, it is a formal theory concerned with describing formal objects and formal links, regardless of whether those objects belong to physics, psychology, engineering, economics, or any other field you can think of. In this way, systems theory becomes a kind of a universal language. It allows us to describe how things relate and interact no matter what domain we are exploring. And this brings us beautifully to the figure I have shared, a visual guide that captures the essence of how systems theory views the world. At the center of the diagram sits the object under study. This object might be a purely physical, like a machine part, a cell, or a planet, or it might be social, such as community, business, or even an idea. Systems theory, both physical and social objects with the same principles are treated. It offers universal language to describe the connection between these objects and everything around and within them. Above the object in the figure lies the environment. This environment serves as a container for the object which is under study. It represents everything external that surrounds and affects the object. The environment could be physical, or, for instance, like the atmosphere around a machine, or it could be social and cultural, like the economic climate surrounding a business. Between the object and its environment, the diagram shows interactions. And it's these interactions have been shown as double-headed arrows. These remind us that the object and its environment influence one another. It is not one-way link. There could be, in some cases, there could be one-way links, but generally we treat them as a two-way link and we call that as interaction. The environment sends inputs to the object and the object sends outputs back into the environment. For example, a tree takes sunlight and nutrients, which are inputs, and releases oxygen and shade as outputs. A business receives market demands and regulatory constraints and responds by producing goods and services. This constant exchange defines the object's existence and its behavior. Below the object in the figure, we find another important layer, which we call it as the internal structure of the system. Here, I have shown components and interactions. No object is truly indivisible. It's usually composed of smaller parts that interact among themselves. Think of a car. It is a single object, yet inside it are subsystems like engine, brakes, and electronics, all interacting to make the car function as a whole. Similarly, in a social system like a university, you find departments, faculties, and administrative units working together through countless interactions. The figure shows arrows pointing in both directions between the object and its components, just like the object and its supercomponents or containers, and between the objects and its environment. This conveys a crucial insight from systems theory. Influences move in both directions. The environment affects the object, but the object can also change the environment as well as parts and its environment. Internally, components shape the behavior of the whole, but the whole system can also influence the behavior of its components. This is where concepts like feedback loops come into play. For instance, a company might reorganize its departments if the market environment shifts, while the performance of those departments also shape how the company functions in the market. The figure demonstrates that system theory is not restricted to any one domain. Whether our object is a physical phenomena like a charged sphere, a complex social structure like a bank, or a human mind, the same principles apply. We identify the object, explore its environment, map its internal components, and study the interactions that weave it all together. Finally, the figure hints at the nested nature of systems. The environment shows in the diagram can itself be viewed as an object within a larger system. Likewise, each component inside the object can also be treated as a smaller system or a subsystem with its own components and environment. This nesting or hierarchy allows us to zoom in or out, studying fine details or broad patterns depending on our purpose. Objects of this kind are called as holons. A holon has parts and is a part in itself. When we study holons, it is good to concentrate on the holon at hand and how it is connected to containers and what parts it has got in its environment. This mechanism is what I term it as moving one level up and one level down. When you are studying something, you should never jump the levels in the sense that when a particular component or a part or a system or an object is or a holon is under study, you should only look for L1, that is one level up, and L minus 1, that is one level down. Moving beyond the figure, let's consider how systems theory speaks the same universal language across every domain. Imagine you are looking at a charged sphere in physics. You might study how it influences the space around it, how it interacts with other charges, and how it responds to external forces. Now imagine shifting your attention to the human mind. Though it's entirely different from a charged sphere, it too can be seen as a system made up of thoughts, memories, emotions, and behaviors, all interacting and influencing each other. Or think of a bank handling money, people, information, and legal regulations and much more like that. Even here, system theory provides the same language to describe how different elements connect, exchange resources, and adapt to changes. In system theory, we talk about objects and links. Objects can be anything: a person, a machine, an idea, an organization, a molecule, or a market. Links describe how these objects influence or affect one another. These links can involve flows of matter, energy, information, money, or even social influence. A crucial insight from systems theory is that links can be as important as the objects themselves. For example, two cells in the human body are meaningful not only as individual cells but because they communicate through chemical signals. Two firms in an economy matter not only for what they produce but because of how they compete or collaborate. The links determine how systems behave, how they evolve, and how they respond to changes in their environment. Systems theory also emphasizes boundaries. A system always exists within an environment. It takes its inputs from the environment and produces output that go back into the world. The boundary is what defines where the system ends. The environment and the environment begins. The boundary could also be physical, like the walls of a building, or abstract, like rules that govern a social group. While the boundary system consists of components of within the boundary, the system consists of components, smaller parts that interact to create the behavior of the whole. An aeroplane, for example, is a system composed of wings, engines, fuel systems, electronics, and the pilots. Each of these is a component, and how they work together determines how the airplane performs. It is interesting to note that none of the parts which we considered can fly, but the airplane as a whole can fly. We call this as emergence of a property for the system which is bounded by a boundary. A particularly important concept in systems theory is feedback. Feedback happens when outputs of a system loop back and influence its future behavior. Consider a thermostat regulating room temperature. If the room becomes too cold, the thermostat signals the heating element to turn on. When the desired temperature is reached, the thermostat turns the heater off. This is a simple example of a negative feedback, helping the system to maintain stability. In contrast, positive feedback amplifies the changes, sometimes leading to rapid growth or collapse, as in the case of viral videos on social media or financial bubbles in the stock market. Another valuable idea is that systems are often nested within one another. A cell is a part of a tissue is a part of an organ is a part of an organism is a part of an ecosystem. This nesting creates hierarchies and layers, and system theory helps us to navigate these layers. Zooming in and zooming out provides a mechanism both to see the inner structure or inner picture and what we call it as a bigger picture. While systems theory often uses words and diagrams, the mathematics is a close cousin. Mathematics is also a universal formal language. However, mathematics is especially powerful for describing properties, links, and behaviors in a quantitative terms using numbers, equations, and precise calculations. Systems theory, by contrast, is often more qualitative or structural using visual models and conceptual language. However, help, both of them help us to understand the same essential reality that objects are linked, that patterns exist, and that understanding those patterns helps us to predict and shape the outcomes. One of the great strengths of systems theory is its ability to help us tackle complexity. The world today is full of complex problems: climate change, pandemics, economic crisis, technological disruptions, but don't respect disciplinary boundaries. Systems theory offers tools or to map out these complexities, identify key interactions, and spot where the interactions might have the greatest effect. In short, systems theory is much more than an academic subject. It's a way of seeing the world, a reminder that everything is connected and that even the smallest action can ripple outwards in surprising ways. It offers a universal language for understanding objects and links between them, helping us find order in complexity, clarity in chaos, and solutions in the entangled web of the modern life. Thank you for joining me on this journey. There are many more videos to come on systems theory. Please subscribe my channel and visit my website if you are interested in more explorations into actionable knowledge and systems thinking. Thank you. Thank you very much.